Okay, so we're going to start into chapter 2, as I mentioned, sort of in when I posted up there on Canvas. Once again, on Canvas, you will find the chapter 1 lecture. It's like super, not very long at all. There's not a lot in there, so whatever's in that lecture you're responsible for. Most of it is the scientific method, and that's about it. The rest of the chapter is kind of like an intro to chemistry and some other things. So whatever I lectured on there, you are responsible for, so make sure that you take a look at it. Here we're going to start with chapter 2, which is measurements. And when we talk about measurements, the really important part of a measurement is units. And the reason for that is, for example, if I took a measurement and I write something like 100, what am I really talking about at this point? You really don't know. It's really just a number, right? So I could say I have $100, which would be great. Maybe I have 100 pennies, still great. Not as great as $100 probably, but still not too bad. Maybe I have 100 apples, which is great if I like apples. Measurements is pretty much useless if reference for what it means, right? So whenever you write something or take a measurement, you should always have a unit that goes with that number. So you should always have a number and a unit when you take measurements. Otherwise, like I said, it's kind of a useless number at that point because you really don't know what it means. So when we talk about units, there are two kind of types of units that are used around the world. There is the English system is sometimes referred to as the US system. And that is what we kind of use here in the United States. And then pretty much everybody else uses the metric system outside of here. Um, and that's why, for example, right, if you look in your car, it says miles per hour, and sometimes it'll say kilometers per hour, right? Because in pretty much all other countries, they use kilometers as opposed to miles. One is US and one is metric. So it is a big problem, as you can imagine, if people are using, for example, different units to represent things. And in 1960, they had a conference on weights and measures. Sounds like fun. And they basically came up with, excuse me, a unit of measurement that is sort of used in sciences and in chemistry. And that's what is sometimes referred to as the SI unit, or the International System of Units. For all intents and purposes, it's pretty much the metric system kind of one out there. So it's really based off of kind of the metric system. And so sometimes in chemistry, you'll see like the SI unit is this, or the SI unit for this is that. And that is sort of the standard unit. And that's really important, obviously, as the world got smaller in the sense of people doing business in different countries, right? So if we're here in the US and we're using inches, somebody else is using like, meters or kilometers or something like that. That's a real problem if you're trying to put parts together, right? It's not going to fit really well. So sometimes they come up with this sort of international unit. Now, when we talk about and this is a table from your book, it's really important to understand what those units represent. And when we talk about a mass, the SI unit is a kilogram. When we talk about a length, it is a meter. And when we talk about time, it is a second. And temperature is a unit that maybe you're not familiar with, but you will be very familiar with once you're done with chemistry here, and that is Kelvin. And Kelvin is pretty much the winner in terms of temperature units for chemistry. Almost all formulas in chemistry, if you have a temperature and you need to use it, you need to pretty much convert it to Kelvin as kind of the standard temperature unit that we use. And as we'll talk about, Celsius to Kelvin is a very common conversion that we do a lot in here. In addition, moles is sometimes used for the amount of something or the quantity of something. And that is the abbreviation for moles, M-O-L. It's actually M-O-L-E, but it had to abbreviate somehow, so they got rid of the E. So it's really important that you understand when you see a unit or you tell somebody a unit that you understand what it represents. And what I mean by that is I can't tell you how many people have told me that they have 15 kilograms of water as their volume, or for their mass, they have, 10 milliliters of mass. and they don't understand what those units mean. So it's really, really important to understand those units. Now, when we talk about measurements, there are some that we deal with a lot, length, volume, and mass. So let's start with length. The base unit for length is and 1 meter is 39.37 inches. 1 centimeter, which is a very common unit, and decimeter and kilometer. I would say in this class, centimeter, kilometer, you see a lot in chemistry. Millimeter as well, by the way. Millimeter is also another unit that you see a lot in chemistry come about. When we take a 1 centimeter, that equals 0.01 meters, or 1 times 10 to the minus 2 meters, and that's in scientific notation, which we'll talk about as well in this chapter. By the way, that is also the same as saying there are 100 centimeters in 1 meter. And you get that, by the way, by dividing this guy to the other side, basically, and that'll get you to 100, basically. That'll be 1 in that particular case. So you can use either conversion. Either conversion is fine. Some people like the larger number versus like the smaller number. But definitely centimeters to meters is a conversion you should know. Again, as we talked about, responsible to know these conversions. So for sure, make sure you know that one, I would say. Kilometers, 1,000 meters. As I mentioned before, that is also a conversion that pops up a lot. So you definitely want to make sure that you do know those two. Now, when we use something like the metric system, oftentimes we do use prefixes to sort of change the meaning of the value. And we have these prefixes here: mega, kilo, deci, centi, milli, micro, and nano. And I would say in chemistry, definitely you see pretty much most of these as you go through, not only this class, but as you continue on in 1A and 1B, you'll see pretty much all these kind of conversions. I would say for us, like I said, we will probably see a lot of kilo, milli, centi, nano. When you get to 1A, you'll probably see a little bit more of mega and some micro as you continue on as well. But for here, definitely, you should probably know, again, this table is a good one, that sort of box. It is in your book as well. Uh, the meaning is a couple here. Like I said, there's kind of a bigger version of a meaning and more of a scientific notation version of the meaning. And I would say in most tables that you look at or so, they oftentimes will have the scientific notation sort of version of it. And I would say this is probably misused the most by people. And people always do these conversions backwards when they go to do this. So let me just explain sort of how you would use this. I'm going to explain it for this column here so that you can understand what you should do. So for example, let's say we did centi, like we just saw there. And centi there is 10 to the minus 2. And let's just say we were going between centimeters and meters, right? So when you look at like a prefix unit and another unit, to me, I like to call these guy here, this is the base unit. So the meters here is really the base unit. Centimeters here is the prefix unit, right? Because it's centimeters, right? They both have meters in it, basically. So when you see centi is 10 to the minus 2, what that means is in one of the prefix units, that is how many you have of the base unit. And I can't tell you how many people do it just backwards, basically, yeah. And it doesn't matter the base unit. And sometimes people get a little weirded out by that. Like, oh, all I learned was like centimeters and meters. But like if I had centiliters and liters, liters is the base unit here, and the other one's centiliters. Works the exact same way. 1 centiliter is 10 to the minus 2 liters. So it really doesn't matter the base unit. The centi is the important part, and that is always how you should use that. So for example, if I did kilo, which is 10 to the 3, and I did kilometers and meters, That would mean in one of the prefix units, there are 10 to the 3 meters. By the way, the 10 to the 3, the 10 to the minus 2 is scientific notation, and we'll talk about how to punch that in correctly in the calculator a little bit later on here in this chapter. But basically what this number is 1 times 10 to the minus 2, basically written in scientific notation. So if you need to put that into your calculator, as we'll talk about, you would want to put it in like you're putting in 1 times 10 to the minus 2. The 10 to the 3 would be 1 times 10 to the 3 is basically how you would put that in. So again, it doesn't matter if you were doing kilograms and grams. There would be 10 to the 3 grams in 1 kilogram. So again, people always want to kind of go, for example, 10 to the 3 kilograms is 1 gram, and kind of always do it backwards. So you want to make sure you don't avoid that. So for example, if we had, 52 grams and we want to know how many kilograms that was, we would set this problem up, and we'll talk more about it later in this chapter as well, but we would set it up in chemistry, a word that you'll hear a lot of, which is known as dimensional analysis. And dimensional analysis is where we use something like this, which is known as an equality. An equality basically is two things that represent the same amount of something, but they're on different units. And from an equality, we could actually write conversion factors. And conversion factors are just fractions. So we could have 1 kilogram over 10 to the 3 grams, or we could have 10 to the 3 grams over 1 kilogram. These are the two conversion factors that you could get really from that equality. And if we were going to do, for example, that problem, we would start with our 52 grams of whatever it is. And we would actually do what is referred to as dimensional analysis. And dimensional analysis basically is just multiplying and dividing. And you could take it like a fraction. So even though there's nothing really on the bottom of that, the grams are on top. And that's sort of important for us to understand how we get rid of the grams. How we get rid of things in dimensional analysis is opposites cancel. So if you have something on top and you want to get rid of it, you need to put the exact same unit on the bottom. If you have something on the bottom and you want to get rid of it, you got to put the same one on top. So opposites always cancel. So if we were going to choose our conversion factor here, since grams are up on top, this conversion factor right here has the grams on the bottom, and that's what we would want to use. We would say 1 kilogram is 10 to the 3 grams, right? Now, what this will do is essentially when we do the math of it, and what the math of this is, always when you set it up like this, which by the way, this is how they want you to show your work in chemistry at this school, is through dimensional analysis. We're going to do more examples, obviously, later in this chapter. But what happens when you set it up like this is anything that's on top gets multiplied, and anything that's on the bottom gets divided, basically. So anything on the bottom gets divided. So basically, if I was going to punch this into my calculator, I would take my 52 and I would times it by 1, which you don't really need to do, but we'll do it anyways. And by the way, that's all the numbers that are on top. And when you're doing this, you should hit equals at this point. Then I'm going to come back and divide by what's on the bottom, which again, I don't really need to divide by 1, but if you want to, it won't kill. But you would divide by basically 1 times 10 to the 3. And I would divide that by 1 times 10 to the 3 and hit equals. And I will end up with the wrong answer because I times it by 4 instead of 1. You see that? There you go. We'll do that. There you go. To the 3. There you go. We will end up with 0.052. And the units that are left are kilograms because grams on top and grams on the bottom will actually cancel each other out. The reason they cancel each other out is because when you take 2 divided by 2, that equals 1, right? So if you have kilograms up on, or grams up on top and grams on the bottom, it equals 1, and it basically will cancel each other out in this case. Any questions on that? You can if you use the different conversion, which is, yeah. But this is obviously the one that's in the table, which is there's 10 to the 3 grams and 1 kilogram. Other questions on that? All right, and obviously we're going to do more examples of that in a bit here as well. All right. And when we talk about the differences between the metric system and the English system, One of the big ones is, for example, here with length measurements, we use inches, right? And centimeters. And that is a ruler, by the way. And 1 inch is equal to exactly 2.54 centimeters. And as you can see here, this is our centimeters. These are centimeters on the bottom as well. And those are our inches up on top. So when we look at a normal ruler, right, we have a lot of times inches up on top, right? And on the bottom there, we have centimeters. And what are all the little guys on the bottom of a ruler? They're millimeters, yeah. So there's 10 millimeters in a centimeter. So if you look at a traditional ruler, those little guys are the millimeters, yeah. And the big guys that have numbers are usually the centimeters are labeled, and on top, usually have inches. Now, volume is the amount of three-dimensional space that's occupied by a substance. There is one way that you could get a volume of an object. For example, if you have a cube, you could take the length and you could actually, or three length measurements and cube it. So meters cubed is the SI unit for volume. You may say meters is like a length, but if you took a measurement of the length times the width times the height, and these are all three length measurements, for example, of a cube, which you'll do, I think, on Thursday of this week. You can measure each of these in centimeters, for example. And if you take centimeters times centimeters times centimeters, you get what is referred to as a cubic centimeter. And a cubic centimeter is a volume. Each of these individual measurements, these are all length measurements, right? So if you take a length measurement, basically cube it, you will get a volume measurement. So when we talk about cubic centimeters, that is actually a volume. Cubic meters, cubic decimeters, they're all basically volumes that come from a length measurement. As you can see, decimeters cubed is a liter. 1 cubic centimeter is the same as 1 milliliter. That definitely is something that you should know. It is used a lot in chemistry. Sometimes we roll with cubic centimeters, sometimes we roll with milliliters. And again, it's a one-to-one conversion between them. And it is basically the same. We don't use it too much here, but cc is also a cubic centimeter. And that is also, like I said, a cubic centimeter. That is the same as a milliliter in this case. cc is sometimes used in medicine. If you watch any medicine type shows, right? Got 5 cc's of this, right? Doesn't here is an indication for a cubic centimeter, and it is sometimes used. Probably the conversion that you'll do the most in volume is this one right here, liters to milliliters. So 1 liter is 1,000 milliliters. Definitely should know. Definitely should know. Yeah, and obviously, um, and what I mean by that is very, very often when we take actual measurements of volume. This used a lot in chemistry, so definitely make sure that you kind of know those as well. Now, mass is the quantity of matter that's present in an object. Matter is anything that occupies space and has mass, so it's pretty much anything. When we talk about matter, oftentimes we talk about the three states of matter, which is solid, liquid, and gas. And the fun uh, things in chemistry in grams and milligrams. So I would say this chart right here, also from your book, is three very common mass measurements and conversions that we use a lot. There's 1,000 grams in a kilogram, And there's also, by the way, 1,000 milligrams in a gram. So just like we just saw on the previous slide, there's 1,000 milliliters in 1 liter. There would be 1,000 milligrams in 1 gram. So again, those conversions are the same conversion, and it doesn't really matter the unit, or the base unit that we're talking about as well. So definitely grams to kilograms used a lot, and also milligrams as well does pop up a lot in here. Now, there is a difference, by the way, we do use something like this, which is known as a balance or electronic balance there. And we use a balance to measure the mass of an object. And there is a difference between mass and weight. The mass of an object is sort of independent of the force of gravity. And the weight of an object is dependent on the force of gravity. So if you weighed yourself here and you weighed yourself on the moon, you would have different weights, but you would have the same mass if you took the gravity part out of it in each case. And when we weigh something in here, which oftentimes confuses people because the process of getting the mass of an object is the process of weighing something. So people use the word weight a lot when they do that. But you should use the word mass. And the reason for that is the balances and everything take into account the force of gravity and kind of zero it out in a sense. So when you do get or weigh something in chemistry class, you should refer to it as the mass. And again, mass and weight are different as weight is dependent on the force of gravity. Any questions on that there? All right, so I think actually let's take a little 10-minute break or so, stretch your legs, and we'll come back and continue lecturing. Yeah. Okay, we're going to continue on then. First off, any questions on anything we've been talking about here? All right, the next thing we're going to talk about is temperature conversions. And as I mentioned, there's a few different temperature scales that we do come across here in chemistry, but really kind of one that we use the most in formulas and stuff. And the three temperature scales that you should be familiar with is degrees Fahrenheit. And on degrees Fahrenheit or the Fahrenheit scale, water boils at 212 degrees Fahrenheit and it freezes at 32 degrees Fahrenheit. That is the sort of scale we use for like our body temperature and stuff like that when we take our temperature, the temperature outside. Celsius or degrees Celsius is pretty much more of this used by everybody else pretty much. And we use it a lot. And these two numbers are two numbers that you should know, especially as for water. Water boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. So in terms of Celsius, we definitely use Celsius a lot in chemistry. And that is, again, where water boils. And at 0 degrees Celsius, that is where water will freeze, basically. That's sometimes referred to as the normal boiling point of water and the freezing point of water. Now, degrees Celsius or Celsius, we use a lot pretty much as you go to the lab, for example, and you take out your thermometer, it's usually in Celsius. So measurement-wise, in chemistry, we do take a lot of measurements in Celsius. With that being said, the third temperature scale is really the one that we use the most when we're doing calculations. And a lot of times, as we'll talk about, we oftentimes have to convert from Celsius to Kelvin. And Kelvin is abbreviated with a capital K. It is also different than the other two in the sense that we do say degrees Fahrenheit, we do say degrees Celsius. We do not use the degree symbol or say degrees with Kelvin. It's just Kelvin. So if it was 298 Kelvin, that's how you would refer to it. You wouldn't refer to it as like degrees Kelvin or anything like that. So that's a major difference. I would say most of the time in chemistry, you're going to be doing that conversion as you go from Celsius to Kelvin. Occasionally, and a number of times, you'll go backwards. So Kelvin to Celsius to Kelvin, Kelvin to Celsius is probably most of the time what you're going to be doing with the temperature in terms of conversions. And I would say probably 95% of the time, if not more, you're going to do the Celsius to Kelvin. Fahrenheit, frankly, outside of chapter 2, much Fahrenheit popping up anywhere, so really don't see a lot of Fahrenheit, but you should still be familiar with it. And we're going to talk about how to do some conversions, obviously between Fahrenheit and stuff like that. But in reality, in most chemistry classes you take, it's Celsius, and then it's Celsius to Kelvin is pretty much the move. Now, when we look at these, the difference between where water freezes and where water boils on these scales is really how we convert between it. It's about 180-degree difference on the Fahrenheit scale between freezing point and boiling point, and it's about 100 units on the other two. And that's what allows us to sort of convert between them. And to convert between them, these three boxes here are things that you should definitely know. And again, they will not be provided for you, and you will have to do these conversions. So let's talk about the one that will do the most, which is the first box there. And that is the temperature in Kelvin is found by taking the temperature in Celsius and adding 273.15. Now, I'm going to say something. Maybe I shouldn't. I don't know. Well, I'll say it anyways. Most people will roll with 273 when they're doing the conversion. Not here. Again, they're very picky, as I mentioned before. They do want you to use the 0.15. So you do need to use 273.15. I'll catch myself probably not using it sometimes, but make sure that you do use it here. In lab, they use the 273.15. Actually, in lab, they actually rounded to like 273.2 in some experiments. But for us in here, we're going to go with 273.15 because they do want you to kind of include that 0.15, even though it might get rounded off a lot of times along the way, but we'll do that. With that being said, if you did have to go from Kelvin back to Celsius, the temperature in Celsius would be the temperature in Kelvin minus 273.15. So if you had to go backwards, you're going to subtract it. Again, I would say 99% of the time, that's probably what you're going to be using. Occasionally, you'll probably go that way. Sometimes they do want answers in Celsius, and even though you have to do in Kelvin. If you need to do Celsius to Fahrenheit, the temperature in Fahrenheit is 1.8 times the temperature in Celsius plus a 32. That 1.8 is the fraction 9 over 5, so it's the same thing. If you learned the fraction, that's where the 1.8 kind of comes from. If you want the temperature in Celsius, you're going to take the temperature in Fahrenheit minus 32 divided by 1.8. So again, probably outside of this chapter, you're probably not going to see too much of these guys, but you are still expected to know it. It's going to be mainly, up here is really what you're going to be doing with the temperature. Now, if you want to go from, for example, Fahrenheit to you would have to go Fahrenheit to Celsius and then Celsius to Kelvin. And same thing, if you want to go from Kelvin all the way to Fahrenheit, you would have to go Kelvin to Celsius, Celsius to Fahrenheit as well. Now, when we do temperature conversions, and all you are simply doing is taking one temperature value from one scale to the next, there is sort of a general significant figure rule that we follow, and we're going to talk more about significant figures obviously shortly and the main rules that you want to follow. But when you're strictly just doing a temperature to temperature conversion, all you're doing is changing units. The general rule that we follow is you make whatever the original value look like is what your answer should look like. And what I mean by that is if your original value was a whole number, when you do the conversion, you should convert it to a whole number. If your original value went to like the second decimal place, when you convert it, you should take it to the second decimal place. So that is, again, just a general rule in terms of temperature to temperature conversion. There is more strict significant figure rules we're going to talk about later on here. But when you're just doing that temperature to temperature, that's sort of what you want to follow. Whatever that original number looked like is kind of like what your answer should look like as well. Any questions on that there? So why don't you try one, grab your calculators and give it a go here. Temperature is 28.5 degrees Celsius. We want to convert it to Kelvin. Then on second one, we got 41 degrees Celsius. We want to go to Fahrenheit. And lastly, Fahrenheit to Celsius. So take a few moments there, work it out, make sure calculators work. So the first one here, we have Celsius and we want Kelvin. So again, our formula here to get our temperature in Kelvin, we're going to take our temperature in Celsius. Again, we're going to add 273.15. And we're going to put our 8.5 plus 5. 301.65 Kelvin. Again, as we talked about in terms of our answer here, we're just doing temperature to temperature conversion. Our original number went to 1 decimal place. So again here, we actually would want to take this to 1 decimal place. So that's going to give us 301.7 Kelvin in this case. Any questions on that one there? Next one, we're going Celsius to Fahrenheit. And that is something here. Temperature in Fahrenheit is 1.8. Temperature in Celsius plus a 32. So putting our numbers in there, 1.8 times our 41 plus a 32. And if we do a 1.8 times, and actually hit the right button there, 41 plus a 32. That's going to give us on our calculator a 105.8 degrees Fahrenheit. Again, when looking at our original number in this case, it is a whole number. So here we would want to go to a whole number. And again, we're going to round up because we look at the 8, right? So that's going to give us 106 degrees Fahrenheit in this case. Any question on that one there? Lastly, we got 160 degrees. So our temperature in Celsius or Fahrenheit minus a 32 divided by 1.8. That's going to give us a 160 minus 32 divided by 1.8. By the way, just a reminder here, you're going to go 160 minus 32. Make sure you hit equals at the end of that and then divide by 1.8. And you'll get a bunch of 71.111, a bunch of ones, degrees Celsius in this case. Just a reminder, we'll talk about it in just a second, but make sure you don't put too much into your calculator at once if you don't use brackets and stuff like that, so, or parentheses. So more times you hit equals, more time you get the right answer, yeah, as you kind of do parts. Here, also a whole number, so we're going to take it there, 71 degrees Celsius in this case. Any questions on any of those there? Again, as I mentioned, outside of this chapter, probably the top one there is going to be a very common conversion that you're going to do. Yeah. Again, you do need to know how to do those. Will not be provided for you. All right. So if we take a look at these, as we talked about earlier, understanding the type of measurement we're looking at when we are looking at our units. When I see Kelvin, that is what type? That is a temperature, right? And I see liters, that is a volume. Meters is a length, right? Yeah, so that is meters, which is a length. This one here, though, kilograms, is our mass in this case, right? So again, we want to make sure that we just don't write units, but we do understand, you know, what they do represent, and that's really, really important as well. All right. So let's talk a little bit about observations and measurements in a sense. There are two types of sort of observations that we come across. One is qualitative. Qualitative versus quantitative. Qualitative is basically just general observations about something. It's green, it's purple, there were bubbles that started to form, right? You know, rainbows, unicorns, all that kind of stuff, you know, whatever is happening in your beaker, you know, these kind of just general observations about what's going on. Now, that is different than quantitative. Quantitative is when you actually do take a measurement. So it's some type of value that has a number, probably some units, something associated with it. You measure out the mass of an object, right? That's quantitative. You measure out the volume of a liquid, right? Do you want to take a reading quantitatively? Maybe you get a temperature, right? How hot something is. So quantitative is all about measurements. It's all about values and numbers that you have. Qualitative is more about general observations. If you continue on with chemistry to 1B, you do a bunch of experiments which are referred to as qualitative analysis. And in qualitative analysis, because there's no measurements, you actually don't measure anything. You just go like, you know, 10 drops is good, you know, a little bit of scoop of this in there is good. And these are all experiments where you basically just make observations about what happens. For example, you put these two together, you get like a yellow precipitate, or you put these together, you get a white precipitate, solid disappears. So Qualitative is all about those kind of general observations. And again, quantitative is all about measurements. For the most part, the labs that you do in this class and 1A is all about quantitative. And usually when you're in lab and you're doing some type of measurement, you do want to be very, precise and accurate when you are taking those type of measurements. Now, when we deal with numbers, we sometimes in chemistry definitely deal with really large numbers and really small numbers. So, for example, as you can see there, a gram of hydrogen has about 6022. That's a bunch of zeros to read there, but a lot of zeros, as you can see there, hydrogen atoms, and also has a mass that's super small as well, right? Point and a bunch of zeros. Clearly, if you were going to do some type of calculation with those numbers, it's a pretty good chance you're going to lose a few zeros along the way, right? If you try to write all those things down. So usually to handle really large numbers or really small numbers, we like to use scientific notation. And scientific notation, when done properly, has this formula, n times 10 to the n. This is a number between 1 and 10. It cannot be 10. It cannot be over 10. It actually usually is not less than 1 either, but it can't be 1. 1's okay, but not 10, and it can't be over 10. And it is times 10 to a smaller number. And this number up here could either be negative or positive, depending on how many decimal places you need to move to get it to a number between 1 and 10. So for example, if I had 3, 2, 4, 6, and I wanted to write in scientific notation, although there's not a decimal point written in this case, when we're doing scientific notation, we do assume it's like back here. And to get us to a number between 1 and 10, if I went one place, I'm at 324. That is not between 1 and 10. If I go one more place at 32 and some change, that's still not between 1 and 10. If I go one more place, now I am at a number that's between 1 and 10, and that would get me 3 point, if I put my point there, maybe 246 times 10 to the 3, and that's how many places I had to move the decimal point. Now, if I had a sort of smaller number like 0.000432, I would need to go one place, two places, three places, and four places to get to a number between 1 and 10, and that would get me 4.32 times 10 to the, I forgot, 1, 2, 3, 4, negative 4 in terms of that. It is negative because I had to move the decimal place to the right. It is positive because on the top one I had to go to the left. If you want to remember an easier way, I guess, larger numbers, positive exponents, smaller numbers, less than 1, negative exponents. Yeah, so smaller numbers, negative, and positive numbers are larger numbers, or that. You can think of it like a number line, right? You got like 0 and then like plus and negative. So larger numbers are this way, positive exponent. Smaller numbers that way, right, are negative exponents. So that's a way you can remember if you want. We'll also talk about shortly significant figures and scientific notation, but we do want to make sure we write it correctly. Now, more importantly, probably than just writing scientific notation, and where a lot of people really struggle is with the calculator and putting it into your calculator correctly with scientific notation. And sometimes people think they are putting it in correctly and maybe find out later they're not. So let us talk about actually maybe what I think it might be even more important than writing it is how to put it into your calculator. So when you look at your calculator, most scientific calculators should actually have an exponent button. And I would say on most people's calculators, it's going to be one of three combinations. You will either have this button here, which is an EE button. You will either have a EXP button, or if you have some of the newer, I guess they're not really new these days, but they've been out a while, calculators that are kind of two-tone. It has like a main color in the base of it, and on the sides it's kind of white sometimes and like a main color. You will have an actual button that actually says times 10 to the n, and usually those calculators will also have like a little wheel type of deal happening on them as well. These are actually your exponent buttons, and these are the buttons you should use when you punch something into your calculator in scientific notation. Now, with scientific notations, we can, as we just saw, have a positive exponent or a negative exponent. So with that being said, another important couple of buttons on your calculator is what I call your negative button. And on most people's calculators, that is a button that looks like this, or it's a button that sometimes looks like this. It is not your subtract button, by the way. Yeah, so don't use your subtract button for that. Otherwise, you might get an error. So if we were going to put a number into scientific notation into your calculator, let's just say we had 1.25 times 10 to the minus 4. And we'll first talk about these two buttons here. We'll come back to this guy and what you have to do if you have those buttons on your calculator. If you were going to put this into your calculator correctly in terms of scientific notation, you should hit 1.25. And when you do that, up on your display, it probably should say 1.25 clearly at this point. Now you should hit your exponent button, either the EE button or the EXP button, whichever one you have. And when you do that on your screen, one of two things will probably happen. It may put an E there, or it may actually pop up a 10 and a couple of zeros, or it may just go pop up a couple of zeros. One of those three things is probably going to happen. When you hit that exponent button, when you hit this button here, the EE button, it represents this part of the number, the times 10 part of the number, which means you should not hit the multiplication button. By the way, you should not hit like the shift and log button or anything like that, because that is definitely not the right thing to do. All you have left now is the -4 part in this case. And what you would then hit on your calculator is your negative button, not your subtract button, and then 4. And that should put a -4 there, should turn this guy into a -4, should turn this guy into a -4. And that is the proper way to actually punch scientific notation into your calculator. Clearly, if you're going to multiply by another number in scientific notation, you would punch the other number in very similar. If you had a positive exponent, you would do the same thing except leave the negative button out of it, right? So if we had 1.25 times 10 to the positive 4, we would hit 1.25 exponent button and then 4, no negative, obviously, in there. Now, if you have this calculator here, that kind of two-tone calculator, you actually have to do a little bit more work if you want the right answer, which you probably do, I'd imagine. You actually have to put parentheses around every number that you put in scientific notation. So if you had the two-tone calculator that has these buttons, you would actually open a parenthesis. So you would open a parentheses button. You would do the rest of it very similar, 1.25. You then would hit your exponent button. And when you do that on the screen, you would see 1.25, and it will actually go times 10, and you will see your little cursor kind of blinking up on top of the 10 at this point. And at this point, you could kind of do the rest of it. You will go the negative button and 4, and what will happen is now your thing will look something like this, times 10 to the -4, and you got this little blinker now next to the 4 that's up on top. Now, if you try to close the parentheses at this point, you're going to get like a super small parentheses up on top and an error probably on most calculators. So you can't just close the parentheses. That's actually where the will comes into play at this point. You need to then go to your will and actually hit the right-hand button there on the side of your will. And that's going to bring your blinker down to a regular size blinker at this point. And you will end up with something that now looks like this, and a regular size blinker, which you can then close your parentheses at this point. Obviously, you would do this a lot faster than I'm writing it, but once you get the hang of it. It's not a big deal once you get the hang of it, but it's really important to make sure that you punch it in correctly. Any questions on that there? That is really, really where a lot of people screw up, frankly, yeah, is they don't know how to properly punch it into their calculator, and they think they are. A really good way to know that you screwed up the way you punch that into your calculator is if you're doing problems and you have the answers, for example, and your answer is really, really close, the front part, but the exponent part's off. It's because you punched it in incorrect. You did some extra step. All right, so just to make sure our calculators work, why don't we try a couple here? Let's just go, let's do 3.2 times 10 to the minus 2. Let's divide it by 4.5 times 10 to the 9. And then let's take 4.36 times 10 to the minus 7. We'll multiply it by 1.25 times 10 to the 20. Okay, let's take a look. So once again, I'm going to write out how you should kind of punch it in. Again, if you have the first two buttons, second button, pretty much the same thing, just use the parentheses like we talked about. You would go 3.2, you would hit your exponent button. You would then hit your negative button and 2, and that would take care of the first guy. You then would obviously hit your divide button, 4.5, once again, exponent button. This is a positive exponent here, so we don't need the negative, and you would just go 9 and hit equals. And if you do all that, you should get, what we got there? We'll go 7.11, a bunch of ones. And now on your calculator, on mine, for example, it says E minus 12, for example, on my display. So if this was my display, you might have a few more ones. I got tired of writing them, but you got that on your display. So a couple grams here, we would give something like 7.1 times 10 to the negative 12. When we are stating the answer, we would not state it as E negative 12. So you do want to write it as times 10 to the negative 12. By the way, when we have a number that's written in scientific notation, all of the numbers that come before the times 10 part are actually significant. So for example here, 3.2 times 10 to the minus 2, this actually would have two significant figures in this case. Over here, this guy, 4.5 times 10 to the 9, would have two significant figures. And as we'll talk about when we get there, since we're dividing, we actually look at the least number of significant figures, which is 2. And that is why we ended up over here with basically just two significant figures in this case. And again, you want to do the times 10 and minus 12 in this case. A reminder as well that your calculator may not always give you your answer in scientific notation, right? They may just give it to you in decimal form and stuff like that. So you may have to change it. Yes. It's actually the smallest. We'll talk about it, but it's actually the smallest. Yeah. In this case, they're both 2. So we ended up with 2. Yeah. That would be absolutely, yeah. So when we put a circle, I guess, around it, that would be the correct answer in this case. Yeah. In terms of significant figures and the proper way of writing it. Again, sometimes people, when they see that on their calculator, this is what they would write, like 7.1 E minus 12. Don't do that. Again, when you're kind of writing in scientific notation, you should always use the times 10 part. Although in calculators and even things like Excel, we sometimes use E when you're writing it, make sure you use the times 10 part. For the bottom one there, we're going to do the same thing. We're going to go 4.36. Again, we're going to hit our exponent button. We're going to hit our negative button and 7. We're going to hit the multiplication button, 1.2. Once again, exponent button. And again, positive exponent here, so 22. And our equals button in this case. And that's going to get you, looks like a 5.45 E15 on my display on my calculator here. Once again here, we're not going to leave it with the E. We're going to give it as 5.45 times 10 to the 15 in this case. And again, we don't want to leave it like that when we give it. What people sometimes also forget to do is make sure you do look to the right there, because sometimes people just ignore that. And sometimes on people's calculators, I can see how it could be ignored. Sometimes people's display, for example, would give this something like this, like 5.45. There'd be like a big space. There's like a 15 over there at the end or something like that. So sometimes, depending on your calculator, it'll kind of move that exponent somewhere. And sometimes people get in the habit of just kind of looking over here and forgetting about the exponent part. So you want to make sure you don't forget about the exponent part when you are writing it. In terms of significant figures here, because that is 3 and this is 3, in my example here, we should actually have 3 as well for it. So one of the nice things about scientific notation, as we'll talk about when we get to significant figures officially, is you can actually control, for example, how many significant figures you need. And sometimes the only way to give an answer, for example, to the right number of significant figures is to write it in scientific notation. So for example, let's just say the last number, I didn't need 3 significant figures, but I needed 2, right? I could just write it then 5.5 times 10 to the 15. Now I have 2 significant figures, right? If I just needed 1 significant figure, I could go back to the original number and do 5 times 10 to the 15. Now I have 1 significant figure. So by using scientific notation, one of the advantages is, and as you'll come across probably in chemistry, is sometimes when you'll do a calculation, you go, oh shoot, like I need like 3 significant figures. There's just no way to write it in decimal form to 3 significant figures. And the only way you could do it is like scientific notation. So sometimes it's very helpful that way. Yeah. So we'll officially talk about it shortly, but the previous, in the first case we divided, and in the second case we multiplied. So whenever you divide or multiply, the rule is your answer should have the same number of significant figures as whichever number in the calculation is the least. It's always the least or the smallest. In this case, they actually both had the same on each of the numbers, so that's why we ended up there. But it's actually the least number of significant figures when you multiply or divide. When you add and subtract, you actually do a little something different. But multiplying and dividing, that's what you look at. Other questions? All right, so like I said, really important that punching it in correctly into your calculator is really, really important. If you're still not sure where your exponent button is, just come see me at some point. We'll find it on your calculator. But I think that will probably cover 99% of people's calculators. So if we want to write these guys into scientific notation, again, our decimal point is here. So we got to go 1 and 2 places, right? So this would give us 5.68762 times 10 to the 2. Again, it's a large number, positive exponent in this case. Significant figure-wise, this has how many? 6. And that's because the original number, by the way, had 6. And we'll talk more about that obviously in a second. But when you take a number from decimal form or positional notation to scientific notation, or from scientific notation back to like decimal form, you never should really lose significant figures, right? You should maintain the right number of significant figures. Here we would go 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places there. And that's going to give us 7.72 times 10 to the minus 6. Again, small number. In this case, as we'll talk about, that's actually 3 significant figures. 3 significant figures. So again, none of those zeros are important in terms of significant figure. Here, not really written, but it would. This would give us 1.25 times 10 to the 4th, big number, positive exponent, and the 0 not significant, and that is why we got rid of them here. In this case, actually has 3 significant figures on the left and also 3 on the right. And lastly, just 1 place will do us there. 1.35 times 10 to the minus 1 in this case. Any questions on how to write a number in scientific notation, out of scientific notation, but again, more importantly, probably the calculation part. Any questions on that there? All right. All right, so take a moment and write this in proper. All right, so let's take a look here. First one, our decimal is assumed to be here. So 1, 2, 3, 4, and 5. That's going to give us 4.25 times 10. What did I say there? 5, 1, 2, 3, to positive 5. Again, here we'll talk about why these are not significant, and that's really why we dropped them here in a sec. Here we're going to go 1, 2, 3, 4, 5, 6, 7. And that's going to give us 8 times 10 to the minus 7 as that small one. By the way, we also do want to include the units here since we did have some units on each of these. Any questions on that there? Okay. All right, then let's talk about actually taking measurements and uncertainty in measurements. So when we take a measurement, regardless of the type of measurement that we take, there's always some degree of uncertainty associated with it. And that degree of uncertainty does depend on the piece of equipment that you're using. And especially as you get into the lab, the person next to you may actually have the exact same piece of equipment as you do, but the scale on that equipment may be different because it was made by some other producer or maker of it. So when we do measurement, one of the most important things that you should always do is look at the piece of equipment and look at the markings that are on there. And that will allow you to figure out how far you could take a reading. Regardless of that, there is going to be some degree of uncertainty. Frankly, there's going to be some degree of guessing, like estimation, like I think it's there, hopefully. And we're going to talk about how to do that. So let's just do the classic example of a ruler here, maybe. And we'll go on. We'll say these are centimeters, semi-straight. All right. And let's just do the classic arrow there. And we want to measure this red arrow here. So whenever you look at any piece of equipment, be it a ruler, a graduated cylinder, or beaker, whatever it may be, there's always some type of markings. And in my case here, I always think about two types of markings. I call them the large markings. And the large markings are usually the ones that actually have numbers printed on it, basically. And then there's usually some small markings. And the small markings are usually the ones that are actually between the ones that have numbers, but they don't actually have numbers themselves. So here we can see the 1 and the 2 are our large markings, and then all the little markings between the 1 and the 2 are the smaller markings in this case. So the first thing we want to figure out is what is the meaning of the large markings. So we have a 1 here and a 2. And if I subtract that, that is a total of 1 centimeter, right? So each of the large markings in this case represents 1 centimeter. Now, when I look at the smaller markings between the two larger ones, I want to count up how many I have. Now, it's really important when you count that you do count correctly. So to count the smaller markings, where you want to first start counting is after the last large marking. So for me here, that'll be 1. I'm not going to count the 1, but this is where I'm going to start counting. So that's my first small marking. This would be my second, my third, my fourth, my fifth, my sixth, my seventh, my eighth, my ninth. And I want to stop counting at the next large marking, which is the 2 in this case. So I had 10 small markings between the two larger markings. So if you're not sure, you could just do a little math problem. But if I take 1 centimeter and divide it by 10 of the little small markings, that means each of the small markings represents how much? 0.1 centimeters, right, is what each of those little small markings. So if I were to label this, this essentially would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and then obviously it's a 2 as we cross over. First off, any questions on that there? Now, there are certain measurements or values when you're taking a measurement that pretty much everybody should agree upon. And if everybody looked at my badly drawn arrow there that's red, everybody should hopefully agree it is at least 1.3 centimeters, right? It's definitely past the 1.3 marking. It's not to the 1.4 yet, right? And it's definitely not at the 1.3, but it's definitely 1.3. This is what is referred to when you're taking a measurement as all the certain numbers. And when you take a measurement, you should always record all the certain numbers that no matter who takes a look at it, everybody should definitely agree. Now, we could clearly see, as we just talked about, that it's not exactly at the 1.3, not exactly at the 1.4, it's somewhere in between. And that is where the uncertainty is in this measurement, and that is where the estimation is. Now, I could look at it and go, well, I don't know. I think it's kind of like halfway between there, right? Somebody else may look at it and go, I think it's like a little before half, or somebody else may look at it, maybe it's a little past half or something like that. And maybe I think it's, in this case, a little before half. And maybe I record a 4. And obviously my unit with it as well, centimeters. This number that I just recorded is the first uncertain number, it is sometimes referred to. And when you take a measurement, it is always important to record all the certain numbers plus the first uncertain number. And the reason it's important to do that is when you do that, that is what we like to call significant figures. Yeah. Those are all the significant figures in our calculation, which means my measurement right here would have how many significant figures? It would have 3 significant figures, all the certain ones plus the uncertain number. Any questions on that there? Now, it does change, right? So let's just say we had a graduated cylinder. You'll see why I failed art 3 times, but it's not bad for a graduated cylinder-ish. And let's just say we had, I don't know, 20, and we'll do milliliters on this guy here. And we'll put a liquid in there, right? And when you put a liquid into a glass container, you will typically see the liquid curve a little bit. And this curve, badly drawn there, exaggerated drawn there, like a U here, is what is known as a meniscus. And in most cases, the meniscus will actually be this kind of U shape. And when you read a volume, you should always read from the bottom of the meniscus, especially if it's a U. By the way, it can't go the other way, and then you should read from the top, but you should read from the bottom in most cases. The reason for that is something we'll talk about later on in a way later chapter. But what happens is the liquid that's in there and the glass, the attractive force between the liquid and the glass is stronger than the attractive force between the liquid and itself. So capillary action, it rises around the sides there. So it kind of comes up the sides here. And that's why you read from the bottom of the meniscus, because that's unaffected because it's not touching the glass. So that's truly where the volume is. And when you take a volume reading, you should try to get down there and kind of really look at it as best you can. There are certain things that are much easier to see the meniscus, like a graduated cylinder, than if you take a beaker, which has a really big opening, right? And that spreads out the meniscus, makes it really hard to get a proper meniscus look at it. And that's why you should never really use a beaker to measure out volume. It's a terrible device because the meniscus is spread out. And when you go, I filled it to the 50 line and you dump it out, you're like 40 something. It's like way off. Yeah. And that's because it appears it's there. And that's because the meniscus got spread out and you can't really see correctly where it's at. It's also a good thing to think about using the proper device, right? When you take measurements. So if we were to do this, we still want to do the same things we did before, which is our large markings. And in this case, we have a 10 and a 20. And that means our large marking is 10 milliliters in this particular case. We still want to count like we did before the smaller markings. I'll go blue here, I think. So we're going to start here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, we're going to stop there at the next one, which is 10. 10 divided by 10 means the small markings is 1 milliliter, right? 10 divided by 10 gives you 1 milliliter. Right? That means right here is 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So again, when we take our proper reading here, everybody should agree it is at least how much? It's at least 15, definitely, right? So that is definitely what we want to record. That is our certain numbers. But again, it's not exactly at 15. It's not exactly at 16. In this case, it actually, to me, appears further than half, yeah? So maybe like an 8 or a 7, whatever you feel. We'll go 8, why not? And milliliters. This would be my first uncertain number. That means this number would have how many sig figs? It would have 3 significant figures in this particular case. Any questions on that? Now it does matter the scaling. So even though I'm using a graduated cylinder, and what's that? Yeah. Yeah, yeah. So in this case, you would read, and I didn't draw it here, but 0 would be down here. Yeah, so you would read up to down. You're correct. We're going to see an example where you would go the opposite way in just a bit here, but you are correct. It would be 0. So we would be increasing in this case as we go up. And that typically is what happens when you kind of fill it from the top and then it fills up from the bottom. And you usually will read 0 to up. Now, if we took a same graduated cylinder, which has kind of almost similar markings, and again, we'll just kind of start over here with 10, sort of halfway through, and this is our 20. And milliliters. And again, we'll pop it, I don't know, we'll go right about here, maybe. Now, when we take up the large markings, what does my large markings represent here in this one? It does represent 10 milliliters. We got 20 and 10, right? The difference there. Now, when we look at our smaller markings, we got 1, 2, 3, 4, and only 5 in this case. That means the smallest markings in this one means 2 milliliters. If we take 10 divided by 2, that gives us small markings is 2 milliliters. What's that? Uh, where? Here? That's a 2. Yeah. I'm divided by 5. I'm sorry. Thank you. I did the math right. I just wrote the wrong thing. Thank you. I am divided by 5. Thank you very much. I had the answer 2 in my head there. I was right. Thank you. It is 5 markings, so we're going to divide by 5, which will give us 2. And in this case, that would mean this is 12, this is 14, 16, and 18 in this case. So now when we take a reading here, we are between 12 and 14. What is between 12 and 14? It is 13. It is 13 milliliters. And that is the best you could actually do in this case. That would mean this number measurement has how many significant figures? Has only 2 significant figures. What is the uncertain number here? The uncertain number is actually the 3, right? Yeah, so that would be my certain number. And this would be my uncertain number, or my estimated digit, right, would be the 3. The reason we cannot go any further in this case is if we just blow up that section of it, right, 12 and 14, there's no good way to know where 12 stops, where 13 starts, right? There's no real good way to do that. We can't really make an estimate. We could do that in the previous ones because we were only talking, for example, 1.1 to like 1.2, right? So we know that's like 0.1. It's just going to go to 0.2. It's basically an even distribution. We can make that estimate. But here we can't do it. So the best we could do here is 13. So it does definitely depend on the piece of equipment you're looking at, and you should always look at the scaling. Like I was saying earlier, this is a case I've seen it in lab. Somebody pulls out their graduate cylinder, like 10 milliliter, and somebody else pulls out theirs, and they're actually taking different readings or 2 different decimal places because this was made by company A and this was made by company B, and they had actually different scales on them. So it's really important to take a look at. Now, in general, you could take your reading to one more place to the right of the smallest marking. So what do I mean by that? So we go back to our original one. Our smallest marking was to the first decimal place. We could take it to one more place to the right of our smallest marking. Here on this one, our smallest marking was the whole number. We could go one more place to the whole number. That is in general what you could do. You could very quickly figure out how far you could take the reading by adding what is sometimes referred to as the tolerance of your measurement. And to find the tolerance of your measurement, you actually take your smallest marking. So you would take your smallest marking and divide it by 2. See, this time I do want to divide by 2. So we're going to divide that by 2. And that's going to give us 0.05 centimeters. And you can see that is 2 decimal places, and that is where we took our reading to. And here at this school, because they like you to do things a certain way, they do typically in labs want you to include that in your measurement. So in what you would actually write is 1.34 centimeters plus or minus 0.05 centimeters. And that would include the measurement, right, and the tolerance. But if you just quickly divide the small guy by 2, it'll basically tell you how far you should take the reading to. Basically what that's saying is it's usually plus or minus 1 of like the estimated digit. So even though I'm saying it's 1.34, it may be like 1.35, it may be 1.33. That's sort of where the uncertainty sort of lies. If we did that for this guy, we could divide this guy by 2, and that will get us 0.5 milliliters. And we could give our answer correctly, 15.8 milliliters plus or minus 0.5 milliliters. And again, it goes to 1 decimal place. That is how far you should take the reading. This dividing by 2, the smallest digits, the smallest markings, works really great for this as well. If I took this guy and divided it by 2, that gives me 1 milliliter, right? And that works perfect with my 13 milliliters plus or minus 1 milliliter, right? So again, when you take measurements in lab, they definitely want you to include the plus or minus part of it with your measurement. Any questions on that there? And what we're saying here in terms of measurement, this is a pretty crappy measurement in a sense, right? Because I'm saying it's 13, but maybe it's like 14 or maybe it's 12, right? So there's a lot of uncertainty in this measurement versus say the first one where, I'm pretty good all the way out to the second decimal place, right? That's a much better sort of measurement, if you will. Yeah. Yeah, tolerance. Sometimes people call it adding the precision, but I think here they kind of roll with tolerance, and they'll sometimes measure that in a reading. Now, let's just say, for example, we came to our ruler just like we had here at the beginning. So let me just redraw it. So this is basically the exact same ruler we used at the very first. So that means our large markings, right, was 1 centimeter. Our small marking was our 0.1 centimeter. And let's just say I had an arrow in this case where arrow-ish, same thing. It was dead on that marking, basically. We'll go dead on that marking. And that is 1.1, right? 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. So when I record this measurement, should I record 1.4 centimeters, 1.40 centimeters, 1.4000 centimeters, or does it matter? So let's talk about just 2 of these. By the way, I'm going to say this one's no good. I'll talk about why in just a second. When we look at the first way I wrote it, right, this guy, how many significant figures does that measurement have? It has 2 significant figures, right? The uncertain or estimated digit is which number? If it was 2 significant figures, that means I recorded all the certain ones plus the first uncertain one. In this case, the uncertain one would be the 4, yeah? Because this would have to be my certain number, and this would be my uncertain number, right? Or my estimated digit. So basically, when I record it at 1.4, what I'm saying is I think it's 1.4 centimeters, but maybe it's 1.5 or maybe it's 1.3, right? That's where the uncertainty is in that sort of first decimal place. What that basically is saying, if I look at my picture, is, well, I think it's somewhere between here. Yeah. That's a lot of like uncertain area, right? That's a lot of like error basically in there. I'm not really sure where it's at. So when I do this guy, how many significant figures does that one have? It does have 3 significant figures. Which one is the uncertain number? It is the 0 in this case, right? The 1 and the 4 are the certain digits. This would be the uncertain digit. So when I do that, I'm saying I think it's 1.40, but maybe it's 1.41, or maybe it's 1.39, right? The uncertainty is in that digit there. If we go to our picture, that's pretty much in this area, right? In that kind of area. Which one's much better here? And which one's more accurate based on our picture? Yeah, it is this one, right? So when you lop off a significant figure, and we know by taking this guy and dividing it by 2, I should take my reading to 2 decimal places, right? And when you lop off that extra 0, you're actually making your measurement way worse than it should be, right? And you should never do that. So if you happen to find yourself exactly on a marking and you have the ability with that piece of equipment to take it to like the second decimal place, you need to add a 0 to maintain the proper number of significant figures. Otherwise, you just made your measurement pretty crappy in that sense. By the way, the opposite here is if I had this one that I crossed out originally, how many significant figures would this one have? It would have 5 significant figures in this case, right? Which one would be the uncertain 0? The one at the end, yeah? So what this is saying is it's a way better measurement than I could do ever with that, right? And that's no good either, right? So you can't go, I'm way better than it should be, right? And you can't go, I'm worse than it should be. You should do what it says you can do, basically, based on the equipment. So adding zeros sometimes when you shouldn't is just as bad as removing zeros when you shouldn't as well. Because in one case, you're making the measurement way better than it should be. And in the other case, you're making it way worse than it should be. So if you hit something dead on the nose there, you got to give the reading. And obviously here we would still properly record this as 1.40 plus or minus 0.05 centimeters in this case. Any questions on how to take a proper measurement here? Yeah. Yeah. All right. So as I mentioned, it is custom to record all those certain numbers plus a first uncertain number. And by the way, the uncertain number or the estimated digit is not always the last one written, but it is always the last significant figure that is written. So there's a difference in that. You'll see it maybe in some examples here, but the last significant figure should always be the estimated digit. A lot of times that is the last number written, but not always the last number that's written. So let's talk a little bit about accuracy and precision and the difference between accuracy and precision. When we take a measurement, we may be looking at accuracy. And when we look at accuracy, we're trying to look at how close our measurement is to the true value. So if we know what the true value is, we're trying to see how close we got to what it should be. Now, precision, on the other hand, is how close a set of measurements are to each other. And the classic example, as you'll see on the next slide, but I'll just draw my own bullseye board here, dartboard. So let's say we're playing darts, right? The goal here is to hit the center dart, right? So I throw my 3 darts. I hit here, I hit here. I feel like I missed the board there. All right, I missed the board. It happens, you know. Not as big of a dartboard as I thought. Am I accurate if I'm trying to hit the middle? No. Am I precise? I am not, right? I'm all over the place, right? I hit the kind of towards the middle end of the board, and I hit the poor guy sitting next to the board, right? That was sitting there enjoying his day. All right, so I gather up my darts and my dignity, and I go double or nothing. We'll try it again. Not that you should gamble, obviously. And I throw my darts, and I go boom, boom, and boom. Am I accurate? I am not, right? The goal is to hit in the middle, right? Am I precise? I'm precisely not accurate. Yes, I'm very, very precise. Brings up a very good thing that a lot of people can do. You could do the wrong thing every time the same way and get the same answer, even though it's the wrong answer, right? So even though you did it wrong, you're very consistent in doing it wrong and you get the same wrong answer every time. I just want to see if he's going to knock back. No, I'm just kidding. So I pick up my darts, right? And I go triple or nothing in the friendly non-wager thing. And I throw my darts and I go boom, boom, and boom. Am I accurate? Yes, I hit the center, right? Finally, after 3 tries. And am I precise? I am precise. And that's really the goal when you do experiments, right? You want to be accurate. You want to get the right answer, right? And a lot of times when we look at accuracy, we look at something like percent error. It tells us how close we were to like the right answer. And when we do something like percent error, we're looking for something really small because that tells us we did a good job, right? If you had like a 200% error, you pretty much screwed up pretty bad. But if you had like a 0.1% error, you did a pretty good job. It's a really small number. When we look at Precision, what we're looking at is, for example, in an experiment, is it reproducible? Can you do that experiment and get the same answer every single time? And that's oftentimes why in chemistry, for example, when we do experiments, we sometimes do multiple trials to see if it's repeatable or reproducible what you're doing. And that's what precision looks at. And that's what sometimes we look at in terms of like standard deviation, right? How far numbers deviate from each other or percent standard deviation. Any questions on that there? So as I mentioned, accuracy, we definitely want to get to their true value, close to it. Precision, how much they are. Again, that is neither, as we can see. These are all kind of centered together, so we're kind of precisely, but not very accurate. And then as like my example there, we're pretty accurate there and precise. And again, that is the goal, as we talked about, kind of to hit both when you do an experiment. All right, so let's do some readings here. Give us the proper reading here. For the blue line, obviously the numbers go with the bigger line. So that's a 2, that's a 3, and that's a 4 there, right? They kind of got off to the side a little bit. Okay, so again, we're going to look at our large markings. So 2 is there and 3 is there. So our large markings is going to be 1 centimeter difference. Again, if we count our smaller markings starting here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, if we divide that by 10, that's going to give us some small markings of 0. What we got there? 0.1, thank you, centimeters. There we go. And that means that when we look at it here, we got, I guess that's 2.5. And this would be 2.6 and then 2.7 there. So we're between 2.6 and 2.7. So definitely certain number here, 2.6. We definitely could go usually one more place to the right, so not exactly 2.6. So I'm going to go, they're going to probably go with a 9 as my uncertain number in this case. And this obviously would be centimeters. Taking our small marking, dividing it by 2 gives us our plus or minus 0.05 centimeters, which confirms we should go to 2 decimal places, right? So that would look like D there would be a winner in this particular case. Any questions on that there? Yeah. All right, so do this one here. Again, the big numbers go to the guys to the left. Got a little shifty there. Okay, so let's take a look again. We'll go 9 and 10, which is going to give us some large marking there still of 1 centimeter. We should have still our 10 dots there all the way across. And 10. So dividing that by 10 can give us our small of 0.1 centimeters. In this case, the first dot, which is actually past where our arrow is, or our line, is 9.1. So we're definitely less than 9 in this case. We definitely know we could divide that by 2 plus or minus, right, 0.05 centimeters. That means we definitely could go to 2 decimal places. So 9 would be certain for sure. And that's not 2 decimal places. That's not 2 decimal places. And that's definitely not 2 decimal places here. And we're definitely not at 9.1. So it looks like they went with 9.02 centimeters plus or minus 0.05 centimeters in this case. Obviously, we can't go 9.10 because it's nowhere near there, right? So it's definitely got to be less than that. So it's got to be between basically 1 and 9, basically, right, in terms of that. And it clearly looks like it's just past that first line, so closer to the 0 or the 1. Yeah, would be better. Any questions on that? Yeah. So yeah, that gives you the tolerance. It basically gives you what they sometimes call here like the tolerance in the measurement. It's basically how far you can take the measurement. It's where the degree of uncertainty lies. That's just the formula that will always give you basically the proper how far you can take the reading to. It essentially will move you one more place from the smallest marking in most cases to the right. But that will always give you the kind of the proper measurement there. And the way you could kind of think about it too and use it is if you know for sure, if like you're very confident what the smallest markings represent. If you just divide it by 2, you don't have to worry about kind of the number per se, but it will definitely tell you how far you definitely should take the reading to. So it's a good way to kind of use it for that as well. In addition, like I said here, they do want you to record it with every measurement that you kind of make. So C here would be the right one. Any questions on that one? All right, so obviously here, graduate cylinder, like the example we talked about previously. Let's see how we get here. Here we're going to look at our large markings, and we got 30 and 40 in this case. So that is 10 milliliters. Again, looking at it here, we have 1, 2, 3, 4, 5, 6, and then 7, 8, 9, and 10. So dividing that by 10 gives us our small markings of 1 milliliter in this case. Again, we could get our tolerance right by just dividing that 1 by 2. And we do that, that tells us plus or minus 0.5 milliliters. So we automatically know how far we should take the reading to. We definitely should go to 1 decimal place in this case. So because this is 1, each of these, that would be obviously 31, 32, 33, 34, 35, and obviously 36 here if we look at the bottom of the meniscus. So that is where they recorded our certain numbers. Again, looking at the bottom of the meniscus, based on their dash, it's pretty close to the next marking. So they went more than half, which is perfectly fine. Sometimes people think it's always got to be like half or 5. It doesn't have to be 5. Again, if you could clearly see it's closer to like the next marking, again, you go 8 or 9. If you see, like we did in the previous one, is closer to the previous marking, you could, go more towards the 1 or the 2 or the 3 or something like that. So here our 8 would be our uncertain number. And then that is how we would get to our proper one here. This would have how many significant figures? 3. And the uncertain number here is our estimated digit. It is the 8 here, right? And again, uncertainty lies in here. Question on that one there. Super zoomed in. Now, to the earlier question, this is a burette, which is a piece of equipment that you do use a lot in chemistry, and we'll use it towards the end of the semester. Actually, we'll use it maybe towards the beginning as well, but definitely towards the end we'll use it. And a burette is a little bit different. A burette, actually, you fill it from the top. You fill it from the top, and it actually comes out the bottom. Yeah, so you drop it out the bottom. So when you look at a burette, at the very top, it's actually 0. And then you have 1, and then you have 2. So the numbers actually increase as you go down. And that means if you're reading a burette, you would be, for example, if your volume was right about there, for example, that would actually be 1 point something and not 2 point something. Again, it's increasing as you go down. This would be something like 1.50 milliliters, and again, not 2. So it depends on the piece of equipment, depends how the liquid goes out of the piece of equipment. Unlike a graduated cylinder where you pour it out the top and then it gets smaller right as you go down, here you actually fill it and then it goes out the bottom. Yeah, so it's actually dropping as you go down. So you're actually getting to increase the volume as you kind of go down. When you use a burette to take a reading, for example, let's just say you started at, in this example, say you started at 0, and let's say you drained it down to here, right? So if that's 0, that would be 1, that would be 2, that would be 3, that would be 4. And we would end up at 3.5 milliliters. We'll just say we have that many markings to go that far. To find the actual volume you delivered, the volume would be the final volume minus the initial volume. So for example, in this case, in my made-up example, 3.5 milliliters minus 0.0 milliliters means I added in there 3.5 milliliters or whatever was in there. So if you have something like a burette, it does actually increase as you go down. So for example, if we look at this one here, that is 28 and that is 29. So our large marking is still 1 milliliter. Now, when we look at our smaller markings, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if we divide that by 10, we are going to end up with 0.15 milliliters in this case. And I'm sorry, I'm going to divide that by 10, 0.1. I'll get that right. There we go, milliliters. Keep jumping ahead to the tolerance in my head. I'm sorry. So we got 0.1 milliliters. So this would be 28, 28.1, 28.2, 28.3, all the way down to 29 as we come down here. So we could see we're at 28.5, 6, 7, 8, and 9 in this particular case. So when we look at this, when we take our reading, we are not exactly, or they don't feel that the meniscus is exactly at that 29. It's just a hair above it. And we would go 28.85 milliliters. Again, dividing my smallest here by 2, getting us to 0.05 milliliters plus or minus 2 decimal places. So our certain numbers and our first uncertain number right there at the 5, having 4 significant figures in this case. I would say most cases, the burettes that you use, usually 2 decimal places is usually the right one, but you should look at the scale just in case. But in a lot of cases, that is 2 decimal places. So you do have to think about the equipment and how the solution is exiting. Pipettes as well is another piece of equipment where you actually draw the liquid up from the bottom and then you let it go out the bottom as well. So depending on the pipette that you use, sometimes the scaling will go from like 0 to like 5 going up. And sometimes it will go from like 5 to 0, depending on who made it again. So it really does depend. When we use a pipette, for example, at a different school, we use pipettes like that. And sometimes the markings, for example, is 0, 1, 2, 3, 4, and 5. So when people are told to draw up 2 milliliters, since they draw from the bottom, sometimes people go all the way up to the 2. How many milliliters did I just put in there? Yeah, I put way more than 2, right? I actually only needed to go up to like up to here, right? And that would have been 2 milliliters. So again, you want to make sure you think about how the solution gets in there, how it exits, and the markings of what they represent. So sometimes you do have to kind of look at them. All right, let's try this one here. Give it a go. What should be the proper reading here of this burette? So again, we're actually, if you just look at the scale, increasing as you go down. So we want to keep that in mind. And again, that means we're at 20 and 30 for our large, which is going to give us our 10 milliliters. If you count those little markings as best as you can, there should be 10 in there. I'm going to try not to jump ahead on this one. We're going to divide it by 10 and give us 1 milliliter there for our smaller markings. And that would mean in this particular case, this is actually 21 there, 22, and 23, 24, 25, all the way down on the smaller markings in this particular case. So we know that our small marking is 1 milliliter. So if we divide that by 2, it'll give us our plus or minus 0.5 milliliters. So we know we should take it to 1 decimal place in this case. So just by process of elimination, that's going to help us immensely here. We're going to go to 22, which does make sense. I guess if we super zoom in there, we're right around that 22-ish mark in terms of our meniscus in this case. So this would be a case that you might look at and go, hey, it's 22 on the nose and want to record just 22. But again, because we have the ability based on this equipment to go to that first decimal place, we do have to record it as 22.0 milliliters plus or minus 0.5 milliliters. That maintains our 3 significant figures that we should have rather than 2, right? So again, remember that you may have to add a 0 to your measurement or more if it has the ability to go out there. But again, as we talked about, you shouldn't add it if you don't need to, right? Or you shouldn't drop it if you should have it. Question on taking measurements. Yeah. So the key is figure out the markings, figure out large, small. If you just want to jump right from the small divided by 2, figure out how far you can take your reading. And generally, usually is 1 more place to the right of the smallest marking. Make sure you take it and make sure you include the tolerances there in terms of your measurements. Any questions on that there? All right, so since we're talking about measurements here, measurements have significant figures, and that's really where significant figures comes from. And there are rules when we count significant figures. And let's talk a little bit about those rules. So the first rule when you count significant figures is any number that is not a zero is considered significant. When we count numbers, we start left to right, and we start counting once we hit the very first non-zero. So you want to first start counting once you hit the very first non-zero, starting left to right. That in this case would be right here. And then they are all non-zeros, which means this has 4 significant figures. Every one would be significant. The estimated digit or uncertain digit would be which one? It is the 9, yeah. So again, 4 significant figures. The last significant figure would be the uncertain or estimated digit. Now, zeros is what gives people trouble when they're doing significant figures. And there's 3 types of zeros that you come across. There is the leading zero, and those zeros are not significant. So you get as many zeros as you want until you hit the very first non-zero number, and they're not significant. So when we look at this number, none of these zeros are significant. We're not going to start really counting our significant figures until we hit the 4 in this case. And the 4 and the 9 are going to be significant, and that will give us 2 significant figures in this case, with the 9 in this case at the end there being our estimated digit or uncertain digit. Now, we also have captive zeros, or sometimes called trapped zeros, and those actually are significant. And those are zeros that come between 2 non-zero numbers. So again, if we look at this, we're going to start here at the 5 as our first non-zero. These zeros are trapped between a 5 and a 4, which are non-zero, so that makes them significant. And the 4 is significant, so significant, 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 and significant. And this would have 4 significant figures, with the 4 at the end there being our estimated or uncertain digit. The last one is really the one that screws up with people a lot, which is the trailing zeros. And the zeros at the end of a number could be significant, or they may not be significant. And what determines whether or not they're significant or not is there a decimal point in the number? And unlike when we do scientific notation, it needs to be written. So you can't just assume that it's there. So it actually does need to be written in the number. So if we wrote 600 like we got down there, this would have only 1 significant figure. These zeros at the end are not significant because there is not a decimal point written in that number. But if I took my 600 and then put a decimal point there, it would have 3 significant figures in this case. Again, these will now become significant because of the decimal point. For the top one, which one is the estimated digit? It is the 6, again, because the zeros are not significant. So this is what I was talking about before. It may not always be the last number, but it is the last significant figure. So since this has only 1 significant figure, the 6 is actually the estimated digit. Basically, what you're saying with that is, I think it's 600, but yeah, maybe it's 700, or maybe it's like 500. That's a pretty big room for error, right? And so not a great measurement, right? When we do this guy, we're saying, I think it's 600, but maybe it's like 601, or, maybe it's like 599, right? So that's a much better measurement, right? And we're able to go out to more decimal places, or more places than we could in the previous one. Now, what happens if we had 0.00050032000? How many significant figures does that crazy number have? I'm not really sure how you would take that measurement, but the 10. Let's see. We're going to start this way. Are these significant? They're not. They're leading zeros, right? We're not going to really start counting until we hit here at the 5. So we'll see here in a second. I kept going. All right, so that's where we're going to start. That's 1. These are zeros that are trapped, which means they are significant. So we got a significant, 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 significant. 3 is a non-zero significant. 2 is a non-zero, which is significant. How about my zeros at the end? They are significant because way over here, there's a decimal point. So sometimes people think the zeros need to be near the decimal point, and it doesn't. It just need to be anywhere in there. So these 3 would be significant. I don't even know. We got 1, 2, 3, 4, 5, 6, 7, 8, 9 in this, if it could somehow get that measurement, I suppose. So it's really important to write things in proper significant figures when you give the answer. And that is why when we write a number in scientific notation, like we talked about earlier, there's a decimal point always in there, which means, or not always, but in most cases, everybody's significant there. So the 1.20, even if we had 1.20 times 10 to the 2, that is also significant because there is a decimal point. By the way, you want to do sig figs with scientific notation in scientific notation, not when you convert it, even though it should convert the same, but it might not. So how it's written in scientific notation is how many significant figures it should have. Any questions on that there? Okay. Now, lastly here, significant figures do go with measured values and measurements and quantitative type of values, but there are certain numbers that we'll come across which are known as exact numbers. And what are exact numbers? Exact numbers are basically found in two ways. They can either be something that is counted. So the classic example in most books is if you have like 4 apples in a barrel, you're just going to simply count how many apples you have. You're not going to do some type of weird experiment to figure out how many you have. You're just going to simply count them. So that is very commonly how we get exact numbers. The other way is definitions. Like for example, 1 inch is exactly 2.54 centimeters. This is an exact number. And these are a couple of exact numbers, or really everything on this list is sort of ones you should know, but definitely these two for sure. 1 pound is equal to 453.6 grams exactly. 1 foot is 12 inches. So definitions are considered exact numbers. If you remember, we talked about units earlier today, right? And there's two types of units. There are English units and metric units. Is there a question? Specific capacity, Washington. It's 4.184 joules. Yeah, yeah. Joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. Um, so for mass here per grams, it's 453.6. They want to use as exactly, even though it's really not exact, but we'll call it, since they want you to use that number, as an exact conversion. What's the deal with exact numbers? Exact numbers in terms of significant figures can have as many significant figures as you want. They're sort of unlimited, if you will. Now, what that means is, as we'll talk probably next time about, is when you do calculations, and as we talked about, you kind of want to give your answers to the right number of significant figures. When you come across something that is an exact number, you could kind of just ignore its contribution to sig figs because it could have as many as anybody wants to give it. So we kind of ignore exact numbers when we're doing calculations in terms of how many significant figures our answer should have. And we look more at like measured numbers and things that are not considered exact numbers. So what definitions are considered exact numbers? If you remember, we had English and metric kind of conversions. So if you have a conversion that's an English to English conversion, like feet to inches, right? That's considered exact. So any kind of English conversion is considered an exact conversion. If you have any metric to metric conversion, that's considered exact, like we saw earlier, right? 100 centimeters is 1 meter, right? So that is going to be an exact number. It is only typically when you cross over from metric to English that you have to look at it, and it's not considered an exact number outside of, for this class in your chemistry classes here, these guys, yeah, these are considered here as exact numbers. But if it's some other type of English to metric conversion, like maybe you did milliliters to quarts or something like that, you would look at it and have to take it into account when you do your calculation. And obviously we'll talk about that next time.